Welcome to Learning to Engineer. In today's video, we are going to see another method to measure inductance. In the previous videos, we saw Wheatstone's bridge, we saw Maxwell's inductance capacitance bridge, we also saw Hayes bridge. Now, we are going to see another such bridge. This is the Anderson's bridge and this is most useful to find out the value of unknown inductance. We can find out the value of inductance for very low values in this circuit. It is giving better accuracy when compared to Maxwell's capacitance bridge and Hayes bridge. But the method to set up this bridge and then to shield all the points of this bridge is quite complicated compared to others. But if you want a higher accuracy, you could sacrifice on all those points and then try to shield the bridge in some way to give you a better accurate reading. Let's get started. In this bridge, we have 6 branches and we also have a capacitor plus an unknown inductor. By using a value of standard capacitor, we are going to measure the value of unknown inductance in this bridge. Let us say the branch current for this branch is I1 and the branch current for this is I3. The current through this is I2 and this current is IC. At null deflection, we can observe that these two nodes will be at the same potential. So, the current which is entering through this adjustable resistor will directly go into this capacitor and complete this loop. So, this current is also IC. Then, let us consider this current to be I4. We have 6 branches over here. This arm is the unknown arm. We have the value of unknown inductance connected in series with a standard resistance. By adjusting the value of this resistance, we will be able to get the null deflection in this bridge, and once we get null deflection, we will be able to find out the value of the unknown impedance and the unknown resistance of this bridge. Let's start with the derivation. When the bridge is balanced, the potential at this node will be same as the potential at this node. So, you can observe that the resistor R3 is parallel to C at null deflection. So, the voltages across them will be same. This implies that I3 into R3 will be same as IC into 1 divided by j omega C. So, what is the value of the current through capacitance? The current through the capacitance will be j omega C R3 into I3. At null deflection, the current I1 will be same as the current I3 because since there is no current that is passing over here, all the current that is entering into this unknown arm will go straight away into this R3 resistor. So therefore, this capacitance will become j omega C R3 into I1. We are making this to be I1 because we wanted to find out the value of unknown inductance. So, in the entire derivation, you will be able to observe that we will be replacing the current I3 by I1 and we will try to retain the R1 term and the L1 term as much as possible so that we can just isolate them at the end and then find those values. And also, during null deflection, this loop will be closed. If we apply Kirchhoff's voltage law through this loop, we will be getting, let me call this as loop 1. So, I am going to apply KVL at loop 1. I1 into R1 plus j omega L1 plus R1 is equal to I2 R2 plus IC into smaller. Let's also have this aside. I am marking this equation to be second equation and this one to be the first equation. Also, what else can you observe at null deflection? We can say that this path will be parallel with this path. So, R plus C will be parallel with the resistor R4. At null deflection, we can also conclude that R plus the impedance across the capacitance is parallel with the resistor R4. So, this implies that the voltage across these branches is going to be the same. We can also observe that I4 is I2 minus IC just by applying KCL at this node. Okay. So, I can quickly replace it as R4 into I2 minus IC. We are going to stick to the terms of I2 and then I1 in this equation. We have an extra current over here. We have an extra current of IC. So, what can we do? We found out the value of IC. So we are going to substitute for IC in both these equations, here as well as here. Okay, I am marking this one to be equation 3. I am going to substitute the value of IC in both these equations. IC was found to be I1 into j omega C add 3. Let's substitute that into equation 2 as well as equation 3. Let's just take this I1 term to left so that we can isolate I1. So this will become I1 into R1 plus j omega L1 plus small r1 minus j omega C add 3 into small r. This is equal to I2 into R. So now let's substitute the value of IC in the third equation. I1 into j omega C add 3 plus 1 divided by j omega C. IC is j omega C add 3 into I1. So this is the value of IC. IC into R plus 1 divided by j omega C. This is equal to R4I2 minus R4 into IC. IC is nothing but I1 into j omega C add 3. I am just going to take the I1 term to the left side just like how we did in the previous case. So this implies I1 into j omega C R3 into R plus j omega C R3 divided by j omega C plus R4 into I1 j omega C R3. So this is equal to R4 into I2. Let's have the I1 term aside. Here we have a I1. Let's take this common. So this is I1 into, and also you can cancel off this j omega C terms. So this is I1 into j omega C R3 into capital R plus R3 plus j omega C R3 into R4. So this is equal to R4 into I2. If you observe, you will have I2 term in both these equations, and also we will have I1 term. So what can we do now? We have to eliminate one of these terms in order to find out the value of L1 and R1. So we will just find out the value of I2 from this equation and then substitute for I2 over here. Okay, so this implies that the value of I2 will be I1 into the whole term will become divided by R4 j omega into, let's first write the real terms and then the imaginary terms. So this is the whole thing divided by R4. So I1 into R3 by R4 plus j omega C R R3 divided by R4 plus R3 into R4 divided by R4. Okay, we also have a C over here. So what we can do now, we can just cancel this R4 terms. I am just simplifying this and writing it as C into R3. So now we have found out the value of I2. Let's substitute the value of I2 here. Okay, for convenience, let's mark this as equation number 4. Substitute the value of I2 in equation number 4. So we will be getting everything in terms of I1. I1 into R1 plus small r1 plus j omega L1 minus C R3R. This is equal to the whole term into R2. So I can just write it as I1 into R2 into R3 by R4 plus j omega C R3 by R4 plus C R3. Now if you observe, we have I1 term in the left side as well as the right side. So we can easily cancel off them and we can get purely impedance equations. That is why we eliminated the value of I2 here. We replaced it as something times I1, so that when we equate it in the previous equation, we will be getting both these terms in terms of I1 and we can just cancel I1 like this. This implies that R1 plus small r1 plus j omega into L1 minus C R3 into R is equal to R2 into R3 by R4. I am just multiplying R2 inside of all these three terms. So this will become plus j omega into C R R2 R3 by R4 plus C R2 R3. So we have a real term as well as imaginary term in both sides. Let's now equate these two real terms and we will equate these two imaginary terms. So this implies that the value of R1 is equal to R2 R3 R4 minus small r1. Now we have found out the value of unknown resistance perfectly in terms of all the resistances that we know. In case the inductor is a pure inductor and it doesn't have any inductive components, then you will be able to observe that the value of R2 R3 by R4 will be same as R1. So in that case the value of resistance is 0, but that is a very rare case where we find only pure inductors. Now let's equate the imaginary terms and find out L1, which implies the value of L1 is equal to CR3 into R, I am just taking this term here, plus C small r R2 R3 by R4 plus C into R2 into R3. So L1 is equal to, these terms C, R3 and R4 are quite common over here, so we are just taking it out. C R3 R4 into, we do not have a R4 term over here, so I am multiplying it by R4, small r into R4, so that we can, when we just multiply inside the brackets, R4 gets cancelled and you will get the same value, plus small r into R2 plus R2 into R4. So this implies that the value of L1 is equal to CR3 by R4 into, I am just taking the value of small r common, or you can also take R2 common, whichever is easy for you. Both are same. So small r into R4 plus R2 plus R2 R4. Just to make an equation look neat, we are taking this term outside so that it's easier for us to remember this formula. It is CR3 by R4 into R times R4 plus R2 plus R2 R4. Just to get some pattern in it so that we can remember the formula, we are just taking these terms outside. Otherwise, when we have a big formula like this, it's complicated to remember. Now, we have found out the value of L1 as well as R1. Thanks for watching. Do let me know your thoughts in the comment section. If you have any doubts, you are welcome to ask it in the comment section. You can mail to learningtoengineer@gmail.com. Okay, so thanks for watching. Subscribe to my channel for more updates and don't forget to ring the notification bell also, so that once I publish my next video, you will be able to get a notification on your mobile phone. Thank you.